Hello, Year 10s. How's it going, guys? Thanks for coming along. Oh, hey, Callista, first on the chat. Well done. Good job. Okay, guys, so electrolysis lesson 2. I've just got my YouTube window. I'm just gonna wait 1 second to check everything's on. Good job. There we go. We're up and running. That's great. Can close that. The chat's still there. Ah, Jack's been beaten again. Boss. Oh, there's Ian. Amazing. So Ian, I'll mark you as in. We're still missing Henry. If Henry can give me a shout when he gets here, that'd be amazing. Ian, you've been marked on the register. Right, let's crack on, guys. Share screen. Share screen. Let's go for that one. Winner. Right. Okay. So today's lesson. Okay. Today's title is Electrolysis Lesson 2. It's actually a really short sequence of lessons, this, actually. So there should only be 3 lessons in this sequence, and then we're going to move on to the next one, chemical tests. Poor Jack, every time now. So 4 learning objectives today, guys. So number 1, no ionic solutions conduct. Now, I love that one's one of my favorite learning objectives today because we've already done it. Yeah, we already know, but the key thing there really, it's not really a knowledge, it's to be able to explain. So I'm just going to quickly lob that on there. Yeah, so that one there, and we can already do this. Yeah, it's an explain question from the exams. Explain why ionic solutions conduct electricity. And you simply say that there are, when in solution, the ions become free to move, therefore they can carry the charge through the structure. Yeah, those are the key points. Ions, not electrons, but ions. Ions are free to move. Remember, there are no free electrons in ionic compounds. The electrons have been exchanged, they've been swapped during the formation. The non-metal gains the electrons. Reduction is going through reduction, and the metal loses the electrons going through oxidation. But the electrons are not free, they're owned by people. The ions are free to move, to carry charge through structure. Yeah, we've covered this though already. It's just nice to reinforce this. I really have to, I do that a lot, and I'm very repetitive sometimes. But the reason being is because students make very common mistakes. And so I'm just trying to reinforce good practice. The next one, understand what ions are present in solutions. I'm going to put brackets aqueous. Yeah, and that, by the way, is a bit of a leap of faith. I'm sorry about this, guys, and it will make sense, I promise. But I do require you guys to have a bit of a, it's like I said, it's a leap of faith. Next one, understand that reactivity matters. Reactivity only matters in solutions. We'll come to that today, and then predict the products of electrolysis aqueous. It's nice that the word solutions, I just get to replace that now with AQ, because aqueous simply means solutions. Okay, so those are my learning objectives for today. But before I do that, I just want to quickly bring your attention to the lead bromide example. Now, I would usually demo this in school, and it's actually a very important demonstration. So this is not aqueous. This is me just doing, once again, just reinforcing the concept of molten electrolysis. So Edexcel have a fancy for lead bromide. This is heavy Edexcel. Yeah, they love lead bromide. The reason being is it has some beautiful observations. So number 1 is, what does lead bromide look like at the beginning? So lead bromide is an ionic solid. So we're just going to make a couple of notes on this, some bullet point notes. So you can do a little subtitle of lead bromide and put underneath it molten electrolysis. That's your subtitle, electrolysis, like it. To break an ionic compound, to split an ionic compound using electricity. Remember, the ionic is important there. Yeah, and then we're going to do some facts underneath this. So number 1, this is the setup that you would usually see. Now, there is actually something missing from this setup. This is how I would do it in school, but there's actually something missing. Justin Lee. Hi, Justin. So just to explain what's missing is a bulb. You usually add into the circuit here, you usually add a bulb. Now, the reason for this is the bulb is going to let me see. I'm just going to put my little fan on 1 sec. I'm just going to find my little fan. My laptop's going to get very hot, and when it gets hot, it slows down. There we go. We add a bulb. Now the bulb is there to check that the circuit is complete and electrons. Oh, sorry. Yeah, and the circuit is complete. You're not in your class. Why are you here? I don't know who Justin Lee is in, so I don't know why he would be here. But maybe he's got some free time. So why is the bulb there? So just to quickly say, I'd really like you guys, if you can, find a picture of this. If you just type in lead bromide electrolysis, you'll find that picture, and then you can add that to your notes. It's a really good picture. But the bulb there is going to show us something really cool. So now I'm going to switch over to what you see in the beaker when you do this. Not the beaker. It's actually in a crucible. So we can put facts, and this is lead bromide. PbBr2, we all know how that's created now because PB lead is always +2 and Br is 1-. Crossing down, it's nice to see that we're using formulas now on a regular basis. Yeah. So facts. Number 1, lead bromide, PbBr2, as a solid, is a white solid. And it is ionic, high melting point, round about the... Do you know what? I'd quite like to know its actual melting point. So let's see if I can just quickly find that. I hate quoting numbers if I don't know them. So let's see if I can find these. Let's do lead bromide melting point. It will be in the hundreds. Yeah, all melting point. There you go, melting point 370 degrees, but relatively low for an ionic. Yeah, I'm just gonna put brackets, MPT, 370 degrees Celsius. Scary. Okay, so it's a white solid. Now what we're going to do is we're going to heat it. You heat the solid, and it will melt. Now when it melts, it will become almost a white, it'll be glowing orange. Yeah, a glowing orange liquid. And this is because it's crazy hot. Yeah, glowing orange liquid. You wouldn't call it a white or a colorless liquid. It is in reality, but the thing is it's so hot that it's going to glow orange anyway. And then what we do is, now you'll notice in the diagram, the key things here. Number 1, our electrodes, we then place graphite, it's nice to see graphite appearing, graphite electrodes into it. So why do we use graphite? Nice to remind ourselves from the last lesson. It has a high melting point, high MPT. It conducts electricity conducts electricity, and it's inert, unreactive. We don't want this to react with whatever we're making. Yeah? So we place our graphite electrodes in. Now, just to point out that the graphite electrodes are black. This is an important observation. Yeah? Observation that the electrodes are black. Graphite starts off black. Is black. There we go. Okay, so once we then apply the electricity to it, number 1 is you usually don't see the light bulb light up immediately. It usually lights up moments later because most of the time when you add the electrodes, it's not entirely liquid yet. Yeah, once it becomes a liquid, the light bulb then slowly comes on. I'm actually going to share with you a YouTube video of this reaction, of this electrolysis process, because it's actually worthwhile seeing. So the bulb kind of slowly fades on as the electricity begins to flow as the lead bromide becomes molten. Now, once that happens, all of a sudden we see a whole load of observations. So we see observations. Once the electrolysis is running, and this is, I'll tell you why. So here's what's now happening. Yeah, we've got molten lead bromide. We've got PbBr2 liquid with our graphite electrodes in here. Now what we see, now this is, I'm going to put in the battery and then add in my bulb. Once the bulb comes on, I know that electrolysis is happening. Yeah, and it's nice to remember that the large line in the battery is the positive one, the negative one is the shorter. And here's what now happens. The lead 2+, I keep doing that. The lead, try again. The lead, what am I doing? The lead 2+ ions are going to go towards the negative electrode. And the Br minus ions are going to now flow towards the positive. Opposite charges attract. I don't like that that's not as clear as it should be. Yeah, there we go. Let's go over that like that. It's now too fat. Let's make that skinnier. Yeah, so this one now goes over here. Now, when that happens, we see two observations. So number one, over at the positive electrode, we now see dark brown gas. We now see bubbles of dark brown gas appearing and coming out of this electrode. Now, when that happens, the entire liquid actually turns brown because, and you can actually see that, it's starting to turn orange. Yeah, yellowy orange. And then we start seeing brown fumes coming off this. Yes, the observation is we are seeing a brown gas. Now that brown gas, as we all know, is bromine. It's Br2 gas. This is because bromine is a liquid at room temperature, but at this temperature, at 370 degrees, it's going to come out as a gas. So we see at the positive electrode, brown gas. At the negative electrode, we see nothing until we remove the electrode out of the thing, out of the whole setup. Once we remove this, if we take this black electrode and we remove it, we see something really cool has happened. Because what's happened during this process is that the lead 2+ ions, yeah, so it starts off black, and when we remove it, when we then lift this out, we get a rather cool observation. So I'm just going to go lift it out, and here's what you see. As soon as you lift it out, by the way, the electrolysis process stops, but you see this, and I think this is one of my favorite demos because the observations are really, really lovely. Would anyone like to predict what they're going to see on this electrode? What are you going to see at the bottom? Now I'm coloring it all in black, but actually we're going to have a change. We're going to see this. So the question is, what am I trying to show here? Yeah, what has happened to the bottom of the electrode? So right here, it has become silver and shiny. What have I formed? What have I formed at the bottom? I don't know why Julius has retracted something. But what have I formed at the bottom of the electrode during the process? So what we've formed is lead. So we've got silver and shiny lead coating. We have coated, I'll actually put coating. Yeah, well done, Julius, good job. We've actually formed a lead coating. And we can then write the equations for this. So at the positive electrode, hang on, which one was the positive? Panic. Everybody needs to learn panic for electrolysis. So panic is positive anode, negative cathode. Right. So this here, the positive, this one here is the anode. So let's color coordinate this. Positive anode, that's this guy. Yeah, and negative, switch to green, negative cathode, that's that guy. So what's happened at each electrode is this. So first of all, let's do it in red. So the Br minus, I'll make it thicker. So at the positive anode, what we saw was Br minus, make it thicker, Mr. Duncan. Yeah, the Br minus ion is attracted to it because it's positive. Opposite charges attract. Yeah. And now what's going to happen is it's going to become bromine gas. And we know that bromine works in a pair. Yeah, it always has to appear as a pair. So we need to balance for the atoms. So in fact, what we realize is 2 Br minuses are going to hit that electrode and they're going to lose their electrons. Now I'm just going to explain what I'm doing here in terms of balancing this half equation. So when balancing half equations, what I'm actually doing here is balancing for atoms. Number one, balance for atoms. Balance for atoms, which I did first. That there was the 2Br and Br2. So the first step I did. The second step that I did, change my color. Second step I did was balance for charge. Balance for charge. So what I'm now doing is I realize on this side, I've got -2 because I've got 2 Br minuses. And on this side, without the electrons, I've got a side which is 0. So I need to make them the same. And what I do is I add electrons to the other side to balance the charge and bring that down. Now, people often say at this point, why do you put them on that side? The reason why I put them on that side is because, well, these are negative and electrons are negative. They're going to repel each other. They're not going to go on the same side. So they're going to go on the opposite side. And this now becomes -2 as well. So that is now a balanced half equation. And that's the process. It's worthwhile learning that. There's huge value in this process. Balance for atoms, balance for charge. That's it. Right. So what's happening at the negative cathode? So at the negative cathode, panic, I love panic. Negative cathode, what now happens is I'm attracting lead. I'm going to do this in a different color. I did that one in red. Yeah, and let's do this one in, I don't know, let's do this one in green, blue. So the Pb2 plus is attracted to the negative cathode. We can just say that this here is the negative cathode. It gets attracted to it. And what's going to now happen is it's going to gain 2 electrons. Yeah, so why does it gain 2 electrons? Yeah, so if we actually do this as a balancing the half equation, stick to blue, the lead 2 plus becomes lead 0. Let's balance for atoms, 1 lead, 1 lead, we're good. Now balance for charge. I've got +2 on this side and 0 on this side. Right, where are the negative electrons going to be attracted? They're going to be attracted to anything positive. Opposite charges attract. It's going to go onto this side. And I'm going to attract 2 of them. The reason being is each electron is 1 minus, and the lead is 2 plus. So it's going to gain 2 of them to become 0. And then what you realize is here I've got +2. Here I've got -2. When you total that up, it becomes 0, and both sides balance. So it's quite nice to follow the process through, and there's the half equation. And then we can assign oxidation and reduction. We know that oil, I always immediately write down oil rig. I never do anything without it. Oxidation is the loss of electrons. Who's losing? He is. He's losing. Yeah? He's losing because they're being spat out. Yeah? And then reduction, red, is the gain. And the word gain has in it. And these ones here are going in. So this one there, so that's going in. So this one's going to be gaining them. So this one's going to be reduction. So this is reduction. And this here is oxidation. So, and as I said, these observations are so important for me to discuss with you guys because they come up a lot in Edexcel. They love this. They'll say, what observation do we see at the positive electrode? And you'll go, see a brown gas. What do you see at the negative electrode? You see that the graphite becomes silvery shiny. Yeah. Unfortunately, I couldn't find a picture of someone who'd removed the electrode to show you the metal at the end, which is really frustrating. But it's nice to understand it. And it only ever coats it. If you look at this as an example, the coating only happens at where it's up to. So the coating is going to happen on the negative electrode up to there. And then the rest of it will be black. Yeah, it'll be black upwards. And then silver when it's underneath the surface as that's getting coated. And like I said, you have the brown fumes spewing out of this one. It's kind of a cool reaction to see. It's cool electrolysis. That brings us to the end of molten. Now that I've done the lead bromide example that Edexcel really need you to have. So now at this point, I'm going to switch over to aqueous. Right. So, okay, we need a bit of a leap of faith here, which is learning objective number 2. Okay, so ions present in solution. Okay, leap of faith. Ugh. Okay, so subtitle, electrolysis of solution. Electrolysis of aqueous. I always like doing that, state symbols, yeah, of solutions. Okay, so here's the leap of faith. So if you would take something like sodium, let's do sodium chloride as this one you have to know about from Edexcel as well. I'm going to take sodium chloride solid, and sodium chloride solid looks like this: Na plus, Cl minus, Cl minus. I'm just drawing 4. I know that you have to draw 6 in your exam. There we go. So it's a giant ionic lattice. Does viscosity of the molten substance affect the conductivity? Good question. Masaru, yes, the viscosity would affect its conductivity, yes. But if that was the case, you'd just increase the temperature to make it less viscous. It's a really good question. Yes, it does. The lower the viscosity, the thinner the liquid is, the better it will conduct. As the ions become, they can move around more easily and therefore move around more quickly. Therefore, the electrolysis will happen more quickly. Therefore, you're having a larger flow of current. Yes, Masaru. But like I said, you just increase the temperature. The great thing about making something molten is that you can make it as thick or as thin as you like just by raising the temperature. If you have a substance close to its melting point, so a great example is this one. I said we're going to heat this to 370. We're not going to heat this to 370. In reality, in that practical there, we're just going to heat that to about 600, and that will make it really nice and thin. Yeah, the low viscosity. But great observation there, Masaru. I'm very impressed. So if we've got this as a solid, if we now add this to a solute, if we now add this now to water, add to water, what do we see? We see this picture. This is now the picture that everyone now observes. We've got our water, and the ions become free to move around. That there is what makes a solution a solution. Yeah, there we go. They float around. Let me show you this as an animation. It's nice to do so. So as an animation, it's nice to always show you the dissolving process, especially in terms of dissolution. No, not diffusion, dissolution. Let's go ionic. You add this to water, let's speed it up, and the water pulls it apart, and the ions become free to move around. So that's now why it can conduct. So the gray bits, I'm going to now slow that down. So the gray bits are the water molecules, and the colored particles are, of course, your ions, which are now free to move around. I do love this animation. It's got a really cool thing. Look what happens if I now evaporate. If I now evaporate this and speed it up, watch what happens. So the water molecules are slowly disappearing. Now, as this happens, as the water molecules disappear, the ions are going to have less space to move around in. And what's going to happen? They're going to crystallize, and it's going to turn back into the solid that we started with. So you can see the water slowly disappearing, less and less water. And look, the ions are now starting to come back together. And it reforms into the white solid that we recognize. And there's our white crystals. There's our white salt that's been left at the end. So it's kind of nice that, because it just shows you that you can get the salt back by evaporating. I think it's quite a nice animation, that one. And how it started off life as a cube, a salt cube, and then it became like distributed along the bottom of the beaker. So it will just become white crystals all along the bottom of the evaporating dish. It's kind of cool, that. So anyway, the ions are now free to move. Now here's the thing. At this point, you would expect that if I did electrolysis on this now, if I put this through electrolysis, they expected to get exactly the same products. They expected to get sodium and chlorine, but it turns out you don't. And I'll tell you why. So what I'm going to do is I'm going to do expected and reality. So this is what they expected. I'm going to do the expected and reality. So this is what so we're going to do electrolysis, and what they expected to get. This was the expectation. Expected, they thought by doing this, they were going to get sodium metal. Yeah, they thought they were going to get sodium solid and chlorine gas. That was what they thought they were going to get. Exactly what they would get if it was molten. But in reality, what did they actually get? So actually, they got this. And this is something I would usually demo. What they actually got was hydrogen gas, chlorine gas, and sodium hydroxide. They got 3 products, and that's aqueous. And they were like, oh, that's really, really odd. why would I get different products? This is what you would have got. You would have got these two if it had been molten. But when it's aqueous, we get three. We get three products, and only one was one that we expected. So this is aqueous in solution. So the question is why? And here's why. It turned out that because water is special, it actually has more ions in the beaker. So, and I know this is strange, just please, it's a leap of faith here, guys. So if I have a beaker of water, here's what the water looks like. H2O. Everyone knows the formula for water. Everyone knows that. The water molecules are all over the place. Yeah, this is water. But it turns out, because there are so many water molecules, every now and again, one of the water molecules will split in half to form these. So it splits here. And I know this is a big leap of faith, guys. And I know it's like, what? Like, trying to understand why it does this. It's because it can. It's because the problem is there are so many water molecules, when they bash into each other, one of them will break in half. Now, don't get me wrong. It won't last very long. It'll go back together. We can write an equation for this, by the way. This is H2O will fall apart to produce these two. This is actually called the ionization of water. Now, just to tell you, just to make you feel a little bit better. So the question is, how many water molecules do this? And I can tell you. So 1 in 10 million water molecules, 1 in 10 million water, I'm going to put H2O molecules, 1 in 10 million H2O molecules breaks apart, falls. I'm going to put breaks, it's better. Yeah, it's better. Breaks apart. 1 in 10 million. But here's the thing. In a beaker of water, if I had a beaker of water containing 18 grams of water, let's call this 18 grams of water. In that beaker, I can now tell you that there are 6, 0, 1, 1. Right, now I need to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's how many water molecules are in the beaker. Molecules are really, really small. And this is something you find difficult to grasp. That's 20 zeros, by the way, if you're wondering. That's how many water molecules are in the beaker. And if 1 in 10 million of them fall apart, what that means is there are plenty of H plus and OH minuses there. So here's the new picture, right? So this is diagram of aqueous NaCl. So this is, by the way, you only really need this for electrolysis. It's nice to understand it. So here's the beaker, and here's what I've now got in the beaker. I'm going to add solid sodium chloride to the beaker, and it will break apart to form Na plus ions and Cl minus ions. Then I've also got water molecules in here, loads and loads and loads and loads and loads and loads of them. But I also have H plus and OH minus ions. That's what I've now got in the beaker. I've got all of those 5 things. Is everyone okay with that so far? I know this is a leap of faith. I know, and it's hard when I'm not at school to prove this to you. I know it's hard. I'm so sorry. Because in school, I can prove this, you see. We can actually see them. Like, I can actually do practicals to literally show you that these exist. So, since I've got those ions in the beaker, I'm now going to add my electrodes. We're now going to do electrolysis. And what's now going to happen is the ions are all going to move towards their respective electrodes. I'm going to use graphite electrodes. I could use platinum, but, you know, going to put a light bulb in here. There we go. And now here's what's going to happen. So, well, first things first, the long one is the positive electrode, then the short one is the negative. Yeah. So we've got the positive, so hang on, panic, positive anode, negative cathode. So this here is the anode. This is the anode because it's positive. This is the cathode because it's negative. There we go. Right. So now what I can do is I can now show you what all the ions are going to do. So I have got, let's put the ions in and let's color coordinate them. A positive hydrogen. Let's do a positive sodium. Let's do a negative chloride. And let's do a negative OH minus, a hydroxide. Right, where are they all going to go? So the positives are all going to move towards the negative. So the sodium is going to come around here and make its way all the way over to there. And the hydrogen is going to follow suit. Hydrogen's going to get there too. The chlorine is going to, the OH minus ion, I'm doing that because I've got the color up. The OH minus ion is going to form its way over to the anode because it's positive. And so is the chloride ion. Now, at this point in the process, there is now competition. So the question is, so let's look at this from a cathode perspective. Let's do the cathode. Now we know cathode, positive, anode, negative. Can I just point out, I don't know them. I have to run panic every time to remember. People go, do you just know these? And I'm like, no, I don't. All I've got in my head is panic. And I go, positive, anode, negative, cathode. The cathode is negative. Yeah, I just run it using panic every single time. No failure. I'm running the same thing that you are. So at the cathode, which we now know, here's the cathode. And the cathode is a big fat positive electrode. Yeah, hang on, no, negative cathode. You see, I've still got to do it. Isn't that hilarious? If I don't run it, it becomes a 50-50 guess. This is the negative electrode. I'm right underneath that. Negative cathode. Still checking negative. I'm going to put negative electrode. Right. So what's now got to the electrode? We've got two things. We've now got, number one, sodium metal. Sodium ions. So what could happen here is the sodium ion could collect one electron and become sodium metal. That could happen. Let's now look at the other guy. The other guy is H+. And this guy could, number one, it's going to form hydrogen gas. Anything ending in the word gen is in a pair. So the hydrogen needs to collect 2 electrons because I'm going to need 2 of them. Now, here's the cool bit. Only one of these happens. And it's all about reactivity. So in this case, this one happens. This happens. Now, the question is why this happens. Why? Now, the reason why is reactivity. The reason is if you go to the reactivity series, which I stole before the beginning of this lesson, you realize that hydrogen is here and sodium is there. Well, we know that the more reactive metals want to get rid of their electrons more. Well, if we flip that, it means that the less reactive they are, the easier it would be to gain them. And hydrogen is lower in reactivity than sodium. So why does this happen? Hydrogen, answer, hydrogen is lower in reactivity than sodium. Just going to put Na. So gains the electron, the E minus, more easily. And can I just point out, by the way, you could also argue that both of these would happen. You could argue that. But the thing is, if the sodium does happen, if this was created, the hydrogen would just steal the electrons from it. It would just go, if the sodium gained it like that, and now it's gone, I've got my electron back, it's just going to immediately give it over to him. Because the hydrogen's less reactive. So the sodium's just going to pass it over. It'll do a displacement immediately afterwards, so it doesn't happen. So it's all to do with reactivity. So let's now look at the other. By the way, this now explains why hydrogen is the product. It explains our odd observation. Ah, that is now explained. Hydrogen is less reactive than sodium, so I'm going to get the hydrogen gas, not sodium metal. Okay, the next one. What about the anode? So let's now draw a box. What about an anode? So the anode, zoom in. The anode, yeah, what's the charge on? Panic. Positive anode. Right, I'm just going to write that down there. Positive electrode. I'm still running panic. Positive electrode. Right. So this is positive. Let's do this in, I don't know, stick with red. Why not? Yes, go with that. No, let's go for blue. Quite like, I don't know, positive. There we go. So what's going to go here? So what's going to go here is the chloride ion. Let's do that in a different color. I did that in brown, didn't I? So the chloride ion. Now, the chloride ion could lose its electrons and become chlorine. Let's balance it. 2 chlorides will be needed to make a chlorine molecule. So it's going to spit out 2 electrons. Yeah? That could happen. Or, alternatively, the OH minus ion could get there. Now, this is much more complicated. Yeah, this is much more complicated. If the OH minus ions are going to get there, and I'm sorry for this one, guys, you don't actually need to know this. This bit is outside your realms. If you get this, you're going to rip the electron off it. Well, if you rip the electron off it, this entire thing is going to it's going to fall to pieces. It's tempting to draw it out and actually show you what this looks like. Yeah, looks like this. This is the hydroxide ion. And there's the extra electron right there. There's the extra that has come from the sodium in this case. Or no, it's the one that came from, because this is what water looks like. This is what water looks like. Yeah, there's water. Everybody is happy. Hydrogen has its full outer shell because it's only got the first shell, which only holds 2. And oxygen has its full outer shell of 8. Well, if you then pull off that H, yeah, it has that extra electron there. So that's the extra. So that's what makes it minus. And if you rip that off, the problem is it's going to become very unstable and it falls apart. And what you actually get is hydrogen gas again. Now, I don't want to get lost in this, because in order to balance that half equation, it becomes really, really messy. I can do. It's actually balancing an alkali to boot. So what's actually going to happen is I'm actually going to get water being produced as you guys are going to ask me to do this. I don't, and you actually, unfortunately, you actually kind of need this for Edexcel. Right, so just bear with me for a minute, guys. Just bear with me. Because in order to do this, I've got to do a rather odd process. So I've got, right, 2 hydrogens, metal, water for oxygen, don't need it. Hydrogens, I need 2 of them. So I've got to add a H plus onto that side. Yeah. And then I balance for charge. And then I've got to use another equation to cancel it out. Don't ask. I'm building something that you guys should just learn. Yeah. So in reality, that's going to cancel out with that. And that's, and then it becomes super awkward because they then cancel out as well. So it just becomes water becoming hydrogen. Ugh, I don't like it. Right, I'm going to find that one for you because I just think it's just easier, because Edexcel demand you to know this. So let's see if we can find it. The problem is it's actually reversed. It's an absolute nightmare, this. I'm just going to show you. It's actually reversed, which is a nightmare. So hydroxide ion half equation. Images. See, the problem is the whole thing is turned around onto the other side, which is a nightmare. I need to do electrolysis probably. It's going to become turned around. Hydroxide ion half equation electrolysis. Unfortunately, Edexcel, and you just have to kind of learn this one. There it is. Oh, becoming oxygen gas. I take it back. I'm sorry. My bad. You make oxygen. Okay, easy fix. So I'm not, so the OH minus ion, sorry, apologies, you form oxygen, of course you do. Ugh, sorry about that, guys. And then you need 4 of those, and then you need 2 waters, and then you need 4 electrons to balance. Guys, you need to know that one. That one, you've got to learn. I apologize that I've just made a mistake. I hate making mistakes. It's been a while since I've done that half equation. I tend to just kind of skip it. But anyway, so the point being is, in order to do any of these two ions are in competition. So the question is, who's going to happen? And the answer is the chloride does it. The reason, now at this point, students often ask me why, and you can link it to reactivity, but you don't really need to link it to reactivity. Yeah, this ion is more stable than, so the OH minus ion is more stable than that one. So it's actually more to do with stability than reactivity, but you can just simply say that the chloride ion is lower in reactivity than the OH minus. It will lose its electron more easily. That's all it comes down to. Yeah. So that one gets there. So it's worthwhile putting a note onto that. So let's go like this. So chloride ions will lose electrons. Chloride ion will lose electrons, lose electron more easily than OH minus, That's all you need to know. So now, by the way, you do get a small amount of oxygen, a very small amount of oxygen. In reality, you don't even, it's almost unmeasurable, but you do, and that's an annoying thing. That Edexcel done it once, and it really upset me because it wasn't fair. It's really, really mean. I'll show you the question in the exam when we get there. But that actually brings me to the end. So we've now finished the electrolysis, and what's cool is that what we can now realize is, if we go back to the original equation or the original picture, we can see why the products are what they are. So what we realize is that the chloride ion, this guy, that one's going to get to the electron because it loses the electrons more easily, and that one leaves. I'm going to do this a before and after. I think that's actually the best thing to do here. So here's what's now happening. Here's the before and after picture. I know we're running out of time. Yeah, so here's the before and after. So when the electrodes go in, so we had Na plus, we had Cl minus, we had OH minus, and we had H plus. Right, so what's now going to happen is that the H plus, let's give it some, we need to give them some things, so that's not a positive, that's a negative. So the hydrogen goes to there, and the hydrogen leaves as hydrogen gas. Now, of course, that's constantly being put back by the water. Yeah, the chlorine, on the other hand, the chloride ion hits this electrode, and that one turns into chlorine gas, and it leaves. What's left behind in the beaker? Take them away. What's left behind in the beaker is sodium hydroxide, which is why you get your third product. It's a fascinating process. We get 3 products in this electrolysis. By the way, this is called brine. Sodium chloride aqueous. It has a common name of brine. And we do this on a massive industrial scale. And when you do the electrolysis of brine, of seawater, you might have seen it on tuna tins. Electrolysis, you get sodium hydroxide, aqueous. It's left behind in the beaker. You get hydrogen gas, which leaves the beaker as a gas. It bubbles away. And we get chlorine gas that leaves the beaker as well. So the sodium hydroxide is left behind, whereas the other 2, of course, bubble away as gases. So what I want to now do, so I know this is, I'm going to go back to my learning objectives just because I'm coming to the end of my lesson. So what ions are present? We've done that now. Reactivity matters. We get that now as well. Right, we're now up to the last bit of predicting products. So let's do a whole load of aqueous predictions. Right, so we can put aqueous electrolysis predictions. Right, so, and these are only for aqueous. I just want to do aqueous. So let's take an example of, let's do an aqueous, let's do silver, ooh, that's going to be tricky, that one. Yeah, let's go for silver. The problem is I'm going to get stung by that if I do that. Let's do copper chloride, copper 2 chloride. So we're going to add copper 2 chloride into the beaker. Right, so what do I have in the beaker? I have Cu2 plus, Cl minus, H plus, and OH minus. Right, what am I going to get? First thing, compare the reactivity of the positive ions. Right, so where's my reactivity series? I go, ooh, copper is below hydrogen. I'm going to get copper metal here, not hydrogen gas. So this one, so Cu2 plus, copper is lower than hydrogen in reactivity. So what I'm going to see is I am going to therefore make copper, not hydrogen gas. I'm going to make copper solid, copper metal on the electrodes, on the negative electrode. Yeah, on the negative electrode, light bulb. Yeah, on the negative electrode. So I get copper metal. Tick. Next. Oh, Cl minus and OH minus. We know that the Cl minus, it wants to give it away. Now, I know people are going to go, I could never guess that one. I could never use the reactivity series. You're right. Well, that's why you need to know some of them. So, and here's the great rule. You guys need to just learn that this one never does anything. I just want you to learn that. So I'm then going to form chlorine gas. Chlorine Cl2 gas. There you go. So my two products of that are going to be copper, metal, and chlorine gas, all to do with reactivity and the ability to lose electrons. Let's look at another one. Let's do another one. What about let's do aqueous lead bromide. Aqueous lead bromide. Let's do that one. Right. So what ions are we going to have? We're going to have Pb2 plus, we're going to have Br minus, we're going to have H plus, and we're going to have OH minus. We never do the OH minus, so just ignore it. Just ignore it. So we're going to get bromine here. Yeah? So, but which one of these two is going to get there? Right, well, hang on a minute. Reactivity. Where's lead? Where's hydrogen? Hydrogen is lower than lead. We're going to get hydrogen gas and not lead metal. Yeah, so we're going to end up with lead hydroxide. Yeah, so we're going to end up with Br minus, which is going to become bromine, balance the half equation. So we're going to get bromine. We're also going to get hydrogen gas because the hydrogen gas is lower in reactivity. Oh, wrong side. Electrons will be attracted to positive things. Notice they're always on opposite sides in redox. Yeah, but so therefore we're also going to have a third product of left in the beaker is going to be the OH minus ion and lead. We're going to get lead hydroxide, lead 2 hydroxide if you like. There we go. Guys, only one more person has to like the video for it to get 10 likes. Jack, you're so funny. You know, Jack, I don't really do this, Jack, for the likes, but it's cute that you do it. So, guys, I hope that helps. It's really about picking the metal. That's what they're usually wanting you to do. And this now brings my lesson to a close. I know this has been tough. It really is tough. And you're having to have a huge faith in me about the ions. And I'm sorry about that. It's a massive leap of faith. But it's what we see. And the observations then prove the chemistry. So it's something which is we're building and understanding based on observations that we make. Right, guys, I will set you your homework on the chat. Oh my God, someone actually did it. Good job, Chuck. So anyway, guys, I'm going to leave you be at that point. That brings me to the end of my aqueous lesson. Next lesson, I'm going to do an exam question review. Yeah, I'm going to look at, I've made a homework specifically for molten, all from the exam questions. I'm going to make a second homework for aqueous. Yeah, and then, second homework for aqueous. And I'm going to go through both of those in one lesson. Yeah, I'm actually going to, I know that you're going to have an assessed homework. It's only literally 20 marks, it's nothing. But I'll do the exam question review before that. And then we're going to moving on to chemical tests. Guys, I hope you have a nice day, and I'll see you all soon.